We're covering machine learning using this book, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. That's the author of the book. So let's just quickly move on to the first chapter, which is the fundamentals of machine learning. What is machine learning is what we would learn in this chapter. So this chapter just basically talks about the basic machine learning landscape and what is machine learning, how it does what it does, and what can be achieved with the help of that. So first of all, machine learning. Let's move on to what is machine learning. Machine learning is the science of an art of programming computers so that they can learn from data, which means that it gives computers the ability to learn without being explicitly programmed. So traditional programming involves a programmer writing an algorithm, giving an input, and generating an output. But machine learning is different from the traditional programming in the sense that it gives input and output to the machine and the program is generated. Here's the definition. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. Or a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. So let's just decode that definition. There's an experience E that the machine has. There's a task T that the machine is required to perform. There's some performance measure P that measures how well the machine is performing on a particular task. So the definition says that a machine is said to learn when its performance P improves on this task T with some experience E. So there's a task, the machine is performing that. We say that the machine has learned if it performs the task better with experience. So that's just written in some mathematical way, and that's the engineering oriented definition. For example, a spam filter. We use a machine learning program to classify an email, whether it is spam or not. So the machine tries to learn with respect to the training data that it is provided, the examples that the machine is provided. It tries to learn from those examples and classify the email as spam or not. That is machine learning, which means that the machine itself generates an algorithms in order to classify a particular email as spam or not with the help of some training data that we provide to the machine. That is written in this paragraph here. Each training example is called a training instance or training sample. And the task T here is to classify this email as spam or not. The experience is the training data, the experience that the machine gains as it increases, so the training on the training data. And the performance measure P can be defined by the user or us, or the programmer specifically. For example, you can use the ratio of correctly classified emails, that is accuracy. Accuracy can act as a performance measure in order to know how well the machine is performing on this particular task. Accuracy is defined as the ratio of the correct classifications upon the total classifications, which means when provided with a dataset of emails, accuracy is the correctly classified emails upon the total dataset, total number of emails that were provided to the machine. Accuracy hence can be used as a performance measure. So why do we use machine learning? It makes our work easier. So for example, you have this spam classifier. Um, you would try to build an algorithm to classify a particular email as spam or not. But it is very tough to develop this algorithm since there can be 1,000 words that can be present inside a spam email on the basis of which you may want to classify the email as spam or not. So first you would look at what the typical spam email looks like. It may consist of any of these words: credit card free, amazing, discount, for you, and many other such words. There can be thousands of such words present in a spam email, tend to come up a lot in the subject. Perhaps you'll notice that there are a few patterns in the sender's name and the email's body and so on. So this is what the programmer does if it has to build it, if he or she has to build an algorithm in order to classify an email as spam or not. So we'll have to look at all the words that are present that are common in the sender's name, the email body, etc. Then we try to write a detection algorithm for these kind of words for each of these words. And then our program would flag these emails as spam if there are a number of these kinds of words present inside the email or not spam. Then we would test the program again and again, and then we repeat the steps 1 and 2. So this is what we do. Study the problem, gain some insights into what the problem is. For example, here we're just taking into account an email spam classifier. So we're looking at the words that are repeatedly occurring in the spam emails. So that is what we do in studying with the problem step. Then we try to write some rules on the basis of which our program classifies the email as spam or not. Example here, we are recognizing these patterns that are present inside the spam emails, and if a few of these patterns are occurring in a particular email, then we classify it as a spam email. Then we evaluate our program, perform it again and again, perform these two steps again and again, evaluate again and again until it gives a good performance, and then we try to launch the program. So this is what we're doing if we want to write an algorithm to classify an email as spam or not. But since the problem is not trivial, your program will likely become a long list of complex rules pretty hard to maintain. In contrast, a spam classifier built on machine learning techniques automatically learns which words and phrases are good predictors of spam by detecting unusually frequent patterns of words that are present in the spam examples compared to the ham examples. The program is much shorter, easier to maintain, and most likely more accurate. So this is the traditional approach where we're studying the problem, writing some rules, evaluating in order to build a spam classifier. But with machine learning, we just tried some steps and just provide the training data to the machine learning classifier, and it is able to classify a particular email as spam or not by just learning from the training data that is provided to the machine by the user or by a programmer. In contrast, let's just read this paragraph again. In contrast, a spam classifier built in machine learning techniques automatically learns which words and phrases are good predictors of spam by just detecting the unusually frequent patterns of words that are present in the spam examples compared to the ham examples. So this program is much shorter, easier to maintain, and more likely more accurate. This is what the machine learning approach looks like. Just study the problem, train ML algorithm, feed the data, evaluate the solution, analyze the errors, and then launch once we have a good evaluation metric. Moreover, if spammers notice that all their emails contained for you are blocked, they might start using you instead. A spam filter using traditional programming techniques would need to be updated to flag for you. But the machine learning model itself learns, since if we train the machine learning classifier on an online data set is the one which is where the machine learning algorithm is simultaneously updated regularly by addition of data. But in the traditional programming, we'll have to change these patterns once the spammer changes its text in the email, we'll have to update it manually. But for the machine learning algorithm, as and when the data gets updated, the algorithm updates itself, and these words are automatically detected, and the overall program is updated. Another area where machine learning shines is for problems that are either too complex for traditional approaches or have no known algorithm. For example, consider speech recognition. Say you want to start with simple and write a program capable of distinguishing the words 1 and 2. You might notice that word 2 starts with a high pitch sound till. So you could hard code an algorithm that measures high pitch sound intensity and use that to distinguish ones and twos. Obviously, this technique will not scale to thousands of words spoken by millions of very different people in noisy environments and in dozens of languages. The best solution, at least today, is to write an algorithm that learns by itself, given many example recordings for each word. So this is what another example where machine learning performs better than the traditional programming. So, for example, you're performing speech recognition, you want to perform some speech recognition. What would you do if you want to write a traditional program? You'd study the problem first, try to analyze some patterns in the problem, write some code, and then evaluate. So, for example, if you want to distinguish between the numbers 1 and 2, so we recognize that 2 starts with a high pitch sound and the sound t, and the 1 starts with somewhat lower pitch. So we might use that observation in order to classify 1 and 2. But here as well, there are thousands of other words, thousands of other languages wherein 1 and 2 are present, and it's just two words, 1 and 2. And just for distinguishing these two words, traditional programming requires so much of work. And hence, machine learning is the best solution here as well, where we can just write an algorithm that learns by itself by just taking a look at by just training on the recordings, on the training data that we provide, recordings for each word. Finally, machine learning can help humans learn, and algorithms can be expected to see what they have learned. Although for some algorithms this can be tricky. For instance, once the spam filter has been trained on enough spam, it can easily be inspected to reveal the list of words and combinations of words that it believes are the best predictions for spam. Sometimes this will reveal unsuspected correlations or new trends and thereby lead to a better understanding of the problem. So this is what it does. Machine learning also helps humans learn. So once a machine learning algorithm has been trained on enough spam emails, it might give insights into some of the words that are new to humans. So, for instance, once a spam classifier has been trained on spam, it can easily be inspected to reveal the list of words and combinations of words that it believes that are best predictors of spam. And sometimes it will reveal unsuspected correlations or new trends that are unknown to humans, and thereby lead to a better understanding of the problem. Applying machine learning techniques to dig into large amounts of data can help discover patterns that were not immediately apparent. So this is called data mining, where the humans are learning with the help of machine learning. So the best example in order to present data mining is this, where If you're training a machine learning algorithm on spam emails, and at the end it tends to reveal some unsuspected correlations in new trends. So this is where we are learning with the help of machine learning, and that is called data mining, where data is helping us to discover patterns that were not immediately visible. So that's studying the problem, training the algorithm, feeding in the data, and with the solution. Then we inspect the solution, and we get some better understanding of the data set, and we understand the problem better, and we are able to provide some better insights into the problem. To summarize, machine learning is great for problems which existing solutions require a lot of hand tuning or long list of rules. One machine learning algorithm can often simplify the code and form better complex problems for which there's no good solution at all. Using a traditional approach, the best machine learning techniques can find a solution. Fluctuating environments, a machine learning system can adapt to new data, getting insights about complex problems and large amounts of data. So that's a summarization of all of the stuff that we just covered. That machine learning can provide solutions into the problems that are very hard to solve using the traditional programming or would require a lot of work, or complex problem which does not have a solution using traditional programming approach, or can also be deployed into fluctuating environments where we are generally updating the data every few, yeah, updating the data in some time. Getting insights about complex problems and large amounts of data. So that is what we just studied here, data mining. Next, we move on to the types of machine learning systems. Machine learning systems can now be divided into some broad categories, three types of categories. That is human supervision with respect to human supervision, with respect to their learning, and with respect to the data on which they are trained, the classification of data on which they are trained. So, on the basis of human supervision, machine learning algorithms are divided in three parts. So, that is supervised learning, unsupervised learning, sorry, four parts: supervised learning, unsupervised learning, semi supervised learning, and reinforcement learning. Then, on the basis of data and their learning, machine learning systems are divided into online versus batch learning. And on the basis of the type of, yeah, on the basis of data and the type of training data provided to the algorithm, the machine learning algorithms are divided into instance-based versus model-based learning. So that are the three main broad categories on which the machine learning systems are divided: human supervision, type of learning, and data. So human supervision, supervised, unsupervised, semi-supervised, reinforcement. On the learning capabilities, machine learning algorithms are divided into online versus batch, and on the basis of data, instance-based versus model-based. So let's move on to supervised and unsupervised learning. Supervised learning is one where you provide the output and the input to the machine learning model. So the training data consists of the labels or the desired output. For example, this is again taking the example of the spam classifier, providing an instance and we're providing a label if the particular instance is spam or not. So for example, this is an email, so this is not spam. This is an email, this is spam. So this is supervised learning where the label is also provided with the instance. The input and output both are given into the machine learning model or algorithm in order to get the program or the output. Let's learn about classification and regression. So classification is when we have to predict the output in 0 or 1. So we're just classifying the particular instance. The best example is again the spam classifier. We're just classifying whether a particular email is a spam or not. The regression is where we're predicting a particular value. So for example, there are a lot of values that can be predicted, and for example, let's just look at this graph. So this is some feature, this is some value, and these are the data points that are present in the training set. And every data point has a particular Y label. And now you're given just any random data point from this feature's value, and you have to predict a particular value. You're not classifying the particular value into 0 or 1. You just have to predict a particular value, a target numerical value. That is regression or prediction. Let's just read this paragraph. Another typical task is to predict a target numerical value such as the price of a car given features, mileage, age, brand, etc. called predictors. This sort of task is called regression. To train the system, you need to give it many examples of cars, including both their predictors and their labels, that is, prices as well as the features. So these are some of the algorithms that are covered inside the supervised learning. K-nearest neighbors, linear regression, logistic regression, SVMs, decision trees, random forests, and neural networks. These are all examples of supervised learning. Unsupervised learning is just the opposite of supervised learning, wherein we do not provide the label with the training data. So training data is unlabeled, and the machine learns by grouping similar data sets together. So for example, this is the kind of data set that is provided to the machine and tries to group similar people together. And when you give some other instance, for example, another instance is present here, and we'll try to predict this particular group for that instance. These are some of the models that algorithms that are covered under unsupervised learning. K-means, BB-scan, hierarchical cluster analysis, one class SVM, isolation forest, etc. Next, so that's what I was talking about, is just grouping similar instances together. Okay. It is often a good idea to try to reduce the dimension of your training data using a dimensionality reduction algorithm before you feed it into another machine learning algorithm, such as supervised learning algorithm. It will run much faster, the data will take up less disk and memory space, and some cases will also perform better. Okay, let's move on to semi-supervised. So semi-supervised algorithms are where you just provide partially labeled data. So the best example to understand semi-supervised is Google Photos, wherein it tries to group the similar looking faces, but once you provide a label for a particular person, it is able to better perform or better display a particular person, and you're able to find a particular person by their name, and you're able to find all the photos of that person. So that is a semi-supervised. So for example, it is just grouped all the similar instances together, and now you just provide some labels for these. Reinforcement learning is very different. The learning system called agent in this context, we can observe the environment, select and perform actions and get rewards in return. So this is based upon rewarding. So first of all, the machine observes that this is fire, this is water. Then select an action or policy. So it goes to fire and then it's given some points, -50. So that means bad. And it learns from its experience. Then it takes some other action. So this is select action. It selects, okay, fire. And then performs the action, given some points. Then it updates its policy, learns from the experience, updates the policy, iterate it again and again. So reinforcement learning is where the machine learns on its own. It is given a points. It is given some points on how well it is performing. Next is batch or online learning. Batch learning or online learning, these are again machine learning algorithms are classified on how how the training data is provided or how it is learning. So batch learning is also known as offline learning, where the data set is just provided once, the machine trains on it, and it is up and working. Online learning is where you keep updating the data set, and the model keeps updating itself with respect to the updated data set. So another criteria is to classify machine learning systems is whether or not they can learn incrementally from a stream of incoming data. So offline learning is where data set is just provided once, system tries to learn on that, and just it is up and working. Batch learning, the system is incapable of learning incrementally and must be trained using all other available data all at once. Online learning system is this one. So you have trained the machine learning, all of the steps you've performed those, trained this algorithm, evaluated everything, and now you've launched. Now you again feed some new data, keep on feeding some new data on the fly means once it is already implemented. That is, it is learning and running and learning. That is online learning. Next is instance based versus model based. So this is another classification technique in order to classify the machine learning algorithms based upon the data, whether it is instance-based learning or whether it is a model-based learning. So let's just read the instance-based and model-based. One more way to categorize machine learning systems is how they generalize. Let's just highlight this point. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to generalize to examples it has never seen before. Having a good performance measure on the training data is good but insufficient. The true goal is to perform well on new instances. There are two main approaches to generalization: instance-based learning or model-based learning. So this type of classification of machine learning models is based upon generalization, how well the model generalizes to new learning examples. Instance-based learning. Possibly the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by users, not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to flag emails that are very similar to the known spam emails. This requires a measure of similarity between two emails. A very basic similarity measure between two emails could be the count number of words they have in common. The system would flag an email as spam if it has the same number of words. This is called instance-based learning. The system learns the examples by heart, then generalizes to new cases by comparing them to the learned examples or a subset of them using a similarity measure. For example, this figure right here. So it has already learned these instances by heart, and now it is trying to classify some new instances based upon the already learned instances. So if it is, for example, in the spam classifier, if the new emails are identical to the already learned emails, then it classifies them as spam. This is not the best solution, but may work. For example, there's some email that has already been classified as spam, and now there's another email that the machine is trying to classify as spam or not, and it just compares this to one of the already classified emails. And if they are identical, then it classifies as spam. Or another method could be that it just counts the words of all the spam emails and then classifies the new one as spam if it also has the same number of words. This is again not the best example because it is not able to generalize to the new instances that are provided to the machine or the algorithm. For example, in this figure that we just saw, the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. So, for example, this is a new instance, and majority of this um, class consists of these identicals. So that is classified as triangle. Next is model-based learning. Another way to generalize from a set of examples is to build model of these examples, then use that model to make predictions, which is just learn the features of all the already classified instances. Just take in the important features of the already classified, and then try to classify the new instances. This is called the model-based learning, where it is generalizing. New way to generalize from a set of examples is to build a model of these examples and use that model to make predictions. This is called model-based learning. For example, suppose you want to know if money makes people happy, so you download the Better Life Index data from OECD's website, as well as stats about GDP per capita from IMF's website. Then you join the tables and sort by GDP per capita, shows an excerpt of what you get. So this is the GDP per capita and this is the life satisfaction. So a country that has higher GDP per capita has better life satisfaction. Let's plot for a few random countries. This is what you observe. Do you see a trend here? This has a lower GDP, this has a lower life satisfaction. There does seem to be a trend here. Although the data is noisy, that is partially random, it looks like life satisfaction goes up more or less linearly as the country's GDP per capita increases. So you decide to model life satisfaction as a linear function of GDP per capita. This is called model selection. You selected a linear model of life satisfaction with just one attribute, which is GDP per capita. So that's a linear model, and this is the constant one, and this is the slope, and this is the GDP per capita. So you try to build a model out of the already present data set that you have. So here we observe that GDP per capita the life satisfaction is linearly dependent upon the GDP per capita, and we try to make a linear model for this kind of predictions. This model has two parameters, theta naught and theta 1. By tweaking these parameters, you can make your model represent any linear function. So for example, for different values of theta, there are different lines that fit in this data set. So before you can use your model, you need to define the parameters theta naught and theta 1. Can you know which values will make your model perform best? To answer this question, you need to specify a performance measure. You can either define utility function or fitness function that measures how good your model is, or you can find a cost function that measures how bad your model is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training samples. The objective is to minimize this distance. So we'll just study a linear model in detail. This is just an introduction chapter. So we're just rushing through linear model because our main goal is to understand model-based learning and not linear regression model. So this is model-based learning wherein you just classify with respect to a model that is learned from the training instances and not just instance-based where you've already learned things by heart, and then you try to just classify the spam or not based upon the already learned instances. That is model-based learning. You're trying to fit a particular model on the particular data set. So yeah, this is a paragraph about how linear regression model works. So we'll cover this in detail. This is where the linear regression algorithm comes in. You feed it your training examples and it finds the parameters that best fits the linear model for your data, and this is called training the model. In our case, these parameters work the best, where theta naught is 4.85 and theta 1 is around 4.91 10 to the power minus 5. Now the model fits the training data as closely as possible, and that's your linear model that fits this data set perfectly. Finally, ready to run the model to make predictions. For example, say you want to know about how happy grip, and so whatever, and then you just find out. Okay, and for a particular country and a particular GDP, you're able to get the life expectancy, life satisfaction. So that's for a GDP of $22,587, you have a life satisfaction of around 5.96. That's the Python code that is also provided here. That's a linear regression model using scikit-learn. Implementation of the linear regression model using scikit-learn. So scikit-learn is a machine learning library that provides these models that are already built, and you just have to use them. You just have to define them and train them, and you can make predictions out of them. That is it. Then if you, okay, so that's given for some other country where GDP is give this much and the life satisfaction comes out to be 5.77. That's using k-nearest neighbors algorithm. That's another algorithm present in the scikit-learn library. We'll study again that one as well in detail. So if all went well, your model will make good predictions. If not, you may need to use more attributes. So you may need to introduce more features around, like for this example, you may introduce employment rate, health, air pollution, etc. Get more better quality training data, perhaps select a powerful model. In summary, we just studied the data, selected a model, trained that model, and then finally tried to make predictions using that model. This is what a typical machine learning project looks like. In chapter 2, you'll experience this firsthand by going through an end-to-end project. And in chapter 2, work starts. This was just an introduction chapter where you just learned about what is machine learning, what are the different classifications of machine learning algorithms, how does machine learning work, why it is better than the traditional programming, etc. We've covered a lot of ground so far. You know what? Okay, we're summarizing all of it. So you know what machine learning is, why is it useful, what are some of the common categories of machine learning systems, and what a typical project workflow looks like. Now let's look at what can go wrong in learning and prevent you from making accurate predictions. So main challenges of machine learning, in short, since your main task is to select a learning algorithm and train it on some data, the two things can go wrong are bad algorithm and bad data. Let's start with examples of bad data. So the two things that can go wrong while performing a machine learning task on some training data is that you might select a bad algorithm, or you might have some bad data. What is bad data is that you have inconsistent data. Examples, you have missing data present inside your data set, and so on. Or you have insufficient data. For a particular task, you just have very small amount of data to train on. Okay, and I think we should cover this in the upcoming videos, because there are a lot of stuff to, yeah, overfitting and everything. Yes, overfitting, underfitting, all of this. Let's just cover that in an upcoming video. That is a lot of pages right there. This is already becoming a very long video. But let's just go ahead. Insufficient quantity of data. For a toddler to learn what an apple is, it takes a lot of examples for them to easily identify what an apple is. So for a toddler to learn, all it takes is to point out an apple and say apple, possibly repeating this procedure a few times. They might learn, okay, well, this is an apple. This is how machine learning should work, wherein you provide a lot of images, a lot of training data on which it should learn, and sometimes we might have insufficient quantity, which means the algorithm requires some more data to learn. We do not have that much data to provide for the algorithm to learn. That is one of the challenge of machine learning, bad data, insufficient quantity of data. Next is non-representative training data. In order to generalize well, it is crucial that you have data of all types. So for example, this is an example that we've provided, that we had this kind of a data set, and we tried to fit this blue line on this data set, but when we are provided with some more instances, then we find out that this black line rather fits well on the data set than this blue one. This was an example of non-representative data, that some of this data was not at all present and was not introduced to our algorithm, and hence it tries to predict this model, predict these results. The results are guessed based on this blue line rather than considering the new data that was unknown to our model. Next is poor quality data, so that you have some outliers present inside your data, and some features are missing, and you have some missing values. Then irrelevant features, you have a lot of features present inside your data that are irrelevant to the main output that you want to predict. Overfitting the training data is when this is based upon algorithm. So these were the examples of bad data. Now we have the examples of bad algorithms. Bad algorithms is, first of all, the example can be overfitting. So our model is fitting the training data set very well, but is not able to generalize to the new data instances, which means the model is overfitting, which is it performs very well on the training data and is not able to generalize to the new data set. We'll read about overfitting in very much detail in the upcoming video. Underfitting is when it is not able to fit the training data set very well. So let's just summarize all of it. Now, by now, you already know a lot about machine learning. However, we went through so many concepts that you may be feeling a little lost. So let's step back and look at the big picture. Machine learning is about making machines get better at some tasks by learning from data instead of having to explicitly code rules. There are many different types of machine learning systems: supervised, supervised or not, batch or online, instance-based, model-based, and so on. These are broad categories wherein the machine learning models are classified. In a ML project, you gather the training set, you try to study the problem, then you try to feed the data set into your model. The model learns, model trains, and then you try to predict. Then the system will not perform if your training set is too small, or if the data learned about the main challenges of machine learning algorithms, machine learning projects. That the challenges can be bad data or bad algorithm. Bad data is when you have lesser number of instances, you have too many features, you have poor quality of data, you have non-representative data. And bad algorithms is when you have overfitting or underfitting. There's just one last important topic to cover. Once you've trained a model, you want to just hope you don't want just to hope that it generalizes well to the new cases. You want to test your model, how well it is performing for a new data instance. So the only way to know that is using testing. So we need to test the model how well it is performing for the new instances. One way is to just test your model. You can just split whatever data is present with you. You can just split that into training data or testing data. So you can just keep some of the data hidden from the algorithm and use that as a test data in order to know how well it generalizes to this unknown data set. And we can just train the model on this much data out of our data set that we have collected. As these names imply, As these names imply, you train your model using the training set and you test it using the test set. The error rate is called the generalization error or out of sample error. This value tells how well the model performs on the new instances that it has